Okay, so let's dive into how humans think. You know, like how we actually reason in the real world.
Mm.
It's messy
Yeah.
and things change all the time, but we're pretty good at it.
We are remarkably good at it.
Yeah, so how do we make sense of things when we don't have all the information?
Right.
Or when what we thought was true turns out to be wrong? We make assumptions, we jump to conclusions, and sometimes we have to backtrack and revise our beliefs.
It's incredibly dynamic and flexible.
It is. And capturing this kind of reasoning in a formal way has been a huge challenge for logicians for a long time.
Absolutely. Traditional logic systems like classical logic just aren't equipped to handle this kind of uncertainty and change.
Right. They're all about rigid truth-preserving rules. If P, then Q, no matter what.
Exactly. And that's where non-monotonic logic or NML comes in.
And okay, so this deep dive is all about NML, and we're tackling the Stanford Encyclopedia of Philosophy's entry on it.
It's a dense read.
It is. It's a deep rabbit hole, but
Yeah.
I'm excited to see what we can pull out of it.
Me too. It's a rich area with a fascinating history.
So what's the big idea behind NML? Like, what sets it apart from these traditional logics?
Well, the core idea is to develop systems that can model the way humans actually reason, which is often messy, uncertain, and subject to revision.
So instead of assuming that our conclusions are set in stone, NML allows us to retract them when we get new information.
Exactly. It acknowledges that we often reason with incomplete or even inconsistent information, so our conclusions are defeasible.
Defeasible. Okay, so that means they can be defeated or overturned by new evidence.
Exactly like the classic example with Tweety the bird.
Oh yeah, Tweety the penguin.
Right. We might initially assume that Tweety can fly because it's a bird, but then we learn that Tweety is a penguin.
And penguins, of course, are famous for not flying.
Exactly. So we have to revise our initial conclusion.
It seems so natural to us, like we do this all the time without even thinking about it.
We do, but for a traditional logic system, this kind of flip-flopping would be a major problem.
Yeah, it would violate the fundamental principle of monotonicity.
Right, in classical logic, adding new information can only strengthen our conclusions. It can never weaken them.
So NML embraces this non-monotonicity, this idea that our beliefs can change as we get more information.
It does. It allows for the possibility of retracting inferences based on new evidence or even inconsistencies within our existing beliefs.
So it's like acknowledging that our knowledge is constantly evolving.
Precisely. It's a logic of plausible reasoning, where conclusions are supported by the premises without being absolutely guaranteed.
They're tentative conclusions subject to revision.
Exactly. And it's ampliative, meaning it goes beyond what's strictly deducible from the premises.
So it's like making educated guesses and then refining those guesses as we learn more.
That's a good way to think about it.
Okay, but this dynamic nature of NML, it seems like it could get really messy, especially when we have conflicting information.
It can.
Like imagine you hear from one source that a certain politician is a conservative,
Right.
and then another source tells you they're a liberal,
It happens all the time,
especially these days.
especially in the age of social media.
Right, so how do these NML systems even begin to handle these kinds of conflicts?
Well, that's where the real ingenuity of NML comes in. It provides various principles and mechanisms for managing and resolving these conflicts.
Okay, so walk me through this. Like, what are the key principles at play here?
Well, one of the most important is the specificity principle.
Specificity. Okay,
So-
so is that like saying all else being equal, go with the more specific information?
Exactly. It's about prioritizing information that's more tailored to the specific situation at hand.
Like with our Tweety example.
Right. The rule penguins don't fly overrides the more general rule birds fly because it's more specific to penguins.
That makes sense. But what about cases where you have two pieces of information that are equally specific?
Or when there's just no clear winner in terms of specificity.
Right. What happens then?
That's a great question. And it leads us to one of the core challenges in NML, how to deal with unresolved conflicts. And there are two main approaches to this: skeptical reasoning and credulous reasoning.
Okay, those sound interesting. Let's break those down one by one. What's the skeptical approach all about?
A skeptical reasoner is very cautious. They only accept conclusions that hold in all acceptable scenarios or extensions of a knowledge base.
So they're like the ultimate devil's advocate, always looking for potential counterarguments.
You could say that.
Okay, so in the case of our conflicting political views, they would basically just say, I don't know.
Exactly. They wouldn't commit to either conclusion unless they had conclusive evidence one way or the other.
That makes sense. But
Okay.
it seems like it could lead to a kind of analysis paralysis where you end up not believing anything at all.
That is one of the criticisms of the skeptical approach. It can be overly cautious and potentially miss out on valuable conclusions.
So what about credulous reasoning? Is that the opposite?
In a way, yes. A credulous reasoner is more adventurous, more willing to accept conclusions even if they might be conflicting.
So they're okay with a little bit of uncertainty.
They accept conclusions that hold in at least one acceptable scenario, even if there are other scenarios where those conclusions might be false.
So in the political example, they might say, well, maybe this politician is conservative in some contexts and liberal in others.
Exactly. They're not looking for a single definitive answer, but rather exploring a range of possibilities.
So it's like skeptical reasoning is about minimizing the risk of being wrong.
Right.
Incredulous reasoning is about maximizing the exploration of potential conclusions.
That's a good way to put it. Both approaches have their strengths and weaknesses, and the choice between them often depends on the specific application or the goal of the reasoning process.
So it's like there's no one right way to do non-monotonic reasoning.
Exactly. It's about choosing the approach that best fits the situation.
This is fascinating.
It is, and it gets even more interesting as we delve into the specific formal mechanisms that have been developed to implement these non-monotonic reasoning principles.
Right, because we've been talking about these ideas in a very conceptual way,
Yeah.
but I'm curious to see how they're actually captured in concrete logical systems.
Absolutely, and that's what we'll explore next.
So buckle up, everyone. We're going deep into the world of non-monotonic logic.
It's going to be a wild ride. So we left off talking about skeptical and credulous reasoning.
Right, and how they handle those unresolved conflicts.
Yeah, exactly. And there's actually a really interesting challenge that comes up specifically with skeptical reasoning. It's called the drowning problem.
The drowning problem.
Yeah.
Okay, that sounds ominous. What's that all about?
Well, it's this tendency for overly cautious reasoning to reject even plausible conclusions when there are exceptions involved.
Okay, so it's like you're so afraid of making a mistake
Right.
that you end up not believing anything at all.
Exactly. And it can really limit what you can conclude, even when there are perfectly good reasons to believe something.
So can you give an example of how this drowning problem might play out in practice?
Sure, let's go back to our friend Tweety the penguin.
Back to Tweety.
Okay. We know penguins can't fly, right? That's like a classic exception to the bird rule.
Right.
But a really skeptical reasoner might take this exception and kind of run wild with it.
Run wild. Okay. How so?
Well, they might start thinking, well, if penguins don't fly, maybe they don't have feathers either.
Oh, I see.
Or maybe they don't lay eggs.
So the skepticism about one property like flying spills over into other properties even when there's no reason to doubt them.
Exactly. It's like they're drowning in their own skepticism, unable to see the forest for the trees.
That's a great image. So how do NML systems try to address this drowning problem? Do they just accept it as an inherent limitation of skeptical reasoning?
Well, not necessarily. There are various strategies and refinements that try to mitigate it. Some approaches try to limit the scope of the skepticism so it doesn't spread to unrelated inferences.
Okay, so like contain the damage, so to speak.
Right. Others focus on strengthening the criteria for what counts as an acceptable scenario so that only the most robust conclusions get through.
It's like trying to find that sweet spot between being cautious and being open-minded.
Exactly. It's a delicate balance, but it's a crucial one if we want to develop systems that can reason effectively in the face of exceptions and uncertainty.
So we've talked about the drowning problem, and we've touched on some of the strategies for addressing it, but now I'm really curious to see how these non-monotonic principles are actually implemented in concrete logical systems.
Yeah, let's dive into the formalisms.
Let's get into the nuts and bolts of it.
All right, so there's a whole bunch of different formalisms out there, each with its own strengths and weaknesses, but we can kind of group them into a few main families.
Okay, what are the families?
We've got formalisms based on the closed world assumption,
Oh.
inheritance networks,
Hmm.
argument-based approaches,
Interesting.
default logic,
Okay.
autoepistemic logic, and selection semantics.
Wow, that's quite a lineup. Let's start with the closed world assumption that one sounds particularly intriguing.
Yeah, it's a powerful idea, basically. It says that if something isn't explicitly stated or provable within a knowledge base, you can assume it's false.
So it's like saying, if I don't know, it ain't so.
Kind of. It's based on the idea that the knowledge base is complete.
Like if it were true, it would be in there.
Exactly. A classic example is a database of airline flights. Like, if you search for a direct flight from Oshkosh to Minsk and it doesn't return any results.
You'd assume there's no such flight.
Right. You're assuming the database is complete, and the absence of the flight implies its negation.
Okay, but that's a pretty strong assumption to make.
It is, and it doesn't always hold in the real world.
Right, there could be a new flight route that hasn't been added to the database yet.
Exactly. So you have to be careful with the closed world assumption.
It's a powerful tool, but it can lead you astray if you're not careful.
Right. So how is this closed world assumption actually implemented in non-monotonic logic?
Yeah. What are some of the formalisms that use it?
Well, one of the earliest and most influential is called circumscription.
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 Yeah.
It was developed by John McCarthy back in the day, and it tries to capture the closed world assumption by minimizing the extension of predicates.
Minimizing the extent. So, okay, so what does that mean?
It means assuming that predicates only apply to the objects that are explicitly stated or provable.
So like in our flight example.
Right. You would minimize the direct flight predicate to only include the city pairs that are actually listed in the database.
Okay, so you're basically shrinking the set of things that the predicate applies to.
Exactly. And McCarthy formalized this using second-order logic, which is a very powerful logic that allows you to quantify over predicates, not just individuals.
Okay, I remember second-order logic from my logic classes. It's pretty heavy-duty stuff.
It is, and it turns out that circumscription, while being a very elegant idea, can be computationally expensive.
Expensive. How so?
Well, second-order logic is really complex, so it can be difficult to use circumscription in practice for large knowledge bases.
Ah, so it's a great idea in theory, but it runs into some practical limitations when you're dealing with real-world data.
Exactly, and that's why people have developed other, more computationally tractable ways of implementing the closed world assumption.
Like, what are some of those more practical approaches?
Well, another really influential mechanism is called negation as failure.
Negation is failure.
It's sometimes called default negation, and it's a cornerstone of logic programming.
Okay, so how does that work?
It's based on the idea that if you can't prove something, you can assume it's false.
Okay, so it's kind of like a default assumption.
Exactly. It's like saying, if I can't find any evidence that X is true, I'm going to assume it's false.
So it's like a way of simplifying the reasoning process by not having to actively disprove everything.
Right. You only have to revise your assumptions if you encounter evidence to the contrary.
Okay, that makes sense. And is that computationally easier than circumscription?
It is much easier, which is why it's so widely used in logic programming and other areas of AI.
So it's a more practical way of leveraging the power of the closed world assumption.
Exactly, and these are just two examples of how the closed world assumption has been formalized in NML. There are many other variations and extensions, but they all share this basic idea of assuming things to be false unless you have evidence to the contrary.
It's amazing how such a seemingly simple idea can lead to such a rich and diverse family of logical systems.
It is, and it highlights the creativity and ingenuity of logicians in their quest to capture the subtleties of human reasoning.
Right, because we humans are constantly making these kinds of assumptions and inferences all the time.
We are. It's how we make sense of the world.
Okay, so we've explored the closed world assumption. Now let's move on to another family of non-monotonic formalisms.
Sounds good. What's next?
How about inheritance networks?
All right, inheritance networks. Those are a fun one.
Yeah, they sound a bit more visual, a bit more structured than what we've been talking about so far.
They're a way of representing knowledge in a hierarchical way.
Like a family tree.
Kind of more like a taxonomy or, like you said, a family tree.
Okay, it's like with birds and penguins.
Exactly. You could have a node for bird and a node for penguin, and then you draw a link from penguin to bird to indicate that penguins are a type of bird.
Okay, so far so good.
And then you can attach properties to these nodes, like flies for bird
Right.
and doesn't fly for penguin.
Okay, so penguins inherit the property of being a bird, but they override the property of flying.
Exactly. And that's the key idea behind inheritance networks, that properties are inherited down the hierarchy unless they're explicitly overridden.
It's like the specificity principle in action again.
It is more specific information takes precedence over more general information.
But what happens when you have conflicts in the inheritance hierarchy?
That's where things get interesting. Just like with other non-monotonic formalisms, you need ways to determine which inferences are justified.
So are we talking about extensions again?
We are.
Okay, so is it the same idea as with closed world assumption?
It's similar, but the details are different. In inheritance networks, an extension represents a set of beliefs that are consistent with the inheritance relationships and the exceptions.
So you might have multiple possible extensions, depending on how you interpret the network.
Exactly. And some approaches are more cautious, only accepting conclusions that hold in all extensions.
And others are more adventurous.
Right, willing to accept conclusions that hold in at least one extension, even if there are other extensions where they don't hold.
So it's like those skeptical, incredulous reasoners again?
Exactly, they pop up everywhere in non-monotonic logic.
It's a constant theme.
It is. So inheritance networks are a really cool way to visualize and reason about hierarchical information.
Yeah, I can see how they'd be useful in areas like taxonomy and object-oriented programming.
Absolutely, but they do have some limitations.
Like what?
Well, they can't really handle more complex forms of reason, like reasoning about beliefs
Okay,
or situations where you have multiple defaults interacting in complicated ways.
so we need more powerful tools for those kinds of situations.
We do, and that's where formalisms like default logic and argument-based approaches come in.
Okay, let's talk about those, starting with default logic. What are defaults, and how are they different from the rules we've seen in inheritance networks?
All right, so defaults are special kinds of rules that are designed to capture defeasible inferences.
Okay, and what does defeasible mean again?
It means that the inferences can be overturned by new information.
Right, like our penguin friend.
Exactly. So defaults have this specific structure. They have a prerequisite, a justification, and a conclusion.
Okay, so it's like saying if this is true and there's no reason to think otherwise, then we can conclude this.
Exactly. Let's take the classic birds fly example.
Okay.
The prerequisite would be X is a bird.
Okay.
The justification would be it's consistent to believe that X can fly, meaning there's no information saying that X can't fly.
Right, like if X is a penguin.
Exactly. And the conclusion would be X can fly.
So if you tell a default logic system, Tweety is a bird, it'll conclude that Tweety can fly unless it has some reason to believe otherwise.
Exactly. And the way default logic handles these conflicts and inconsistencies is through the concept of an extension.
Extensions again. So are these the same as the extensions we saw with inheritance networks?
The idea is similar, but the details are different. In default logic, an extension represents a set of conclusions that can be drawn from the defaults without running into any contradictions.
So it's like building a little world where all the defaults hold true as much as possible.
That's a good way to think about it.
Okay, so given a set of defaults, you might have multiple possible extensions,
Right.
each representing a different way of resolving the conflicts between them.
Exactly. And just like before we can have skeptical and credulous approaches to reasoning with these extensions.
So a skeptical reasoner would only accept conclusions that hold in all extensions.
Right.
And a credulous reasoner would accept conclusions that hold in at least one extension.
Exactly. It's all about how much risk you're willing to take.
Okay, so default logic seems like a really powerful way to model this kind of tentative revisable reasoning that's so characteristic of human thought.
It is, and it's been used in a lot of different applications, especially in knowledge representation and reasoning.
But it sounds like it could get pretty complex.
It can, especially when you have a lot of defaults interacting with each other. It can be hard to compute those extensions and figure out what the consequences are.
So there are computational challenges.
There are, and there are also some conceptual challenges, like how to handle specificity in a really elegant way.
Right, because specificity seems to be a key principle in non-monotonic reasoning.
It is, and that brings us to another family of formalisms that tries to address this issue in a really interesting way.
Okay, what's that?
Autoepistemic logic.
Autoepistemic logic. Okay, now that sounds like it could get really meta.
It does. It's all about reasoning about your own beliefs.
Like thinking about thinking.
Exactly. It tries to capture the way our beliefs about our own beliefs influence our reasoning.
Okay, so like if I believe that I don't believe something,
Bravo.
then I can't actually believe it.
Exactly. It's like a logical safeguard against self-deception.
I like that.
Yeah.
So how does this work formally?
Well, autoepistemic logic uses a special operator, usually denoted by B, to represent belief.
Okay, so B of P would mean I believe P.
Exactly. And then you can use this operator to express statements like, if I believed P, I would know it, but I don't know it, therefore I don't believe P.
Oh, wow, that's a mind-bending concept, using logic to analyze our own beliefs and how they interact with each other.
It is, and it's a surprisingly powerful tool for modeling certain kinds of non-monotonic reasoning.
So how does this relate to defaults and extensions?
Well, in autoepistemic logic, the key concept is that of a stable theory.
Stable theory. Okay, so what does stable mean in this context?
It means that the agent's beliefs are consistent with their beliefs about their beliefs.
So like there are no contradictions or inconsistencies in their self-reflection.
Exactly. And these stable theories are analogous to the extensions we saw in default logic.
So they represent different possible ways of resolving the uncertainties and conflicts in the agent's beliefs.
Right. And just like with default logic, we can have skeptical and credulous approaches to drawing conclusions from these stable theories.
That's like this idea of multiple possible worlds keeps coming back.
It does. It's a fundamental aspect of non-monotonic reasoning.
This is so fascinating. It's like we're peeling back the layers of the onion of human thought.
We are, and it just keeps getting more and more interesting.
I'm loving this deep dive.
Me too. It's a real mind bender, but in a good way.
Okay, so we've talked about the closed world assumption, inheritance networks, default logic, and now autoepistemic logic.
Quite a journey.
What other families of non-monotonic formalisms are out there waiting to be explored?
Well, there's one more that we should definitely cover. It's called selection semantics.
Selection semantics. Okay, that sounds intriguing. What's being selected here?
It's not about selecting rules, it's about selecting models.
Models. Okay, so remind me what a model is in logic.
Right. So in classical logic, a model is basically a way of interpreting the formulas so that they're all true.
Okay, like assigning truth values to the propositions.
Exactly. And a formula is valid if it's true in all models that satisfy the premises.
So it has to hold true in every possible world where the premises are true.
Right. But selection semantics comes along and says, hey, not all models are created equal.
Not all models are created equal. Okay, I like that.
It's about picking out a subset of the most normal or preferred models and basing our inferences on those.
So instead of considering all possible worlds, you're focusing on the ones that are most likely, given what we know about the world.
Exactly. It's like saying these are the worlds that make the most sense given our common sense understanding of how things usually work.
Okay, so how do you define what makes a model normal or preferred?
Well, there are different ways to do it, but one influential approach uses something called preferential structures.
Preferential structures.
Yeah, it's basically a set of models together with a relation that ranks them in terms of how normal they are.
So like you could have a model where Tweety is a penguin that can't fly,
Right.
and another model where Tweety's a robin that can fly.
Exactly. And the preferential structure might say that the robin model is more normal because it fits the typical bird stereotype.
Okay, so the robin model is preferred because it's more in line with our expectations.
Exactly. And then you can use this preference relation to define a non-monotonic consequence relation.
So how does that work?
You say that a conclusion follows from a set of premises if it's true in all the most preferred models of those premises.
So it's like saying, given what we know and given our assumptions about what's normal, this conclusion is the most likely to be true.
That's a good way to put it. And what's remarkable is that this approach using preferential semantics has been shown to capture the core properties of many other non-monotonic formalisms.
So it's like finding a hidden unity behind the apparent diversity of all these different approaches.
Exactly. It suggests that there are some fundamental principles of non-monotonic reasoning that are common to all these different formalisms.
That's really cool. But you mentioned there are other ways to define preferred models.
There are all sorts of ways. Some approaches use possibility measures, where models are ranked by their degree of plausibility. Others use ordinal ranking functions, which assign numbers to models indicating their level of surprise.
Ordinal ranking functions, okay.
And there are even approaches using conditional probabilities, where you look at how likely the conclusion is given the premises.
Wow, so many different ways to slice and dice the same basic idea.
It's a rich and diverse area, but it's all based on this core idea of selecting the most normal models.
And using those to guide our inferences.
Exactly.
This is fascinating. I'm really starting to see the power and flexibility of selection semantics.
It's a beautiful framework, and it's been incredibly influential in the field of non-monotonic logic.
But now I'm remembering something we talked about earlier, rational monotony, and how it's not always a desirable property.
Right, it can sometimes lead to counterintuitive conclusions.
Exactly. So how does that play out in selection semantics?
Well, it turns out that standard preferential consequence relations, the ones that are defined by those preferential structures we talked about,
Right.
they don't generally validate rational monotony.
Okay, so rational monotony doesn't always hold in those systems.
Right, but there's a special kind of preferential structure called a ranked structure that does validate rational monotony.
Ranked structure. Okay, so
Okay.
it's like a preferential structure, but with some extra constraints.
Exactly. In a ranked structure, the models are arranged in levels like a hierarchy of normality.
Okay, so it's like saying these models are the most normal, these are a bit less normal, and so on.
Exactly. And then a conclusion follows from a set of premises if it's true in all the most normal models of those premises.
So you're only looking at the top tier of models, the ones that are the most likely or the most normal.
Exactly. And these ranked structures have been shown to characterize what are called rational consequence relations.
Rational consequence relations.
Yeah, they're basically preferential consequence relations that also satisfy a rational monotony.
So rational monotony does have a place in selection semantics, but it's a very specific place.
Exactly. It's restricted to these ranked
This is
structures.
getting pretty deep, but I'm following along, I think.
Well, good. It's mind-bending stuff, but it's so cool to see how these different principles and properties all fit together.
Yeah, it's like we're building a giant puzzle of human thought.
We are, and each piece we add brings us closer to understanding how our minds actually work.
Okay, so we've talked about rank structures and rational consequence relations now. What?
Well, the foundational work on selection semantics by Krauss, Lehman, and Magidor has been incredibly influential.
Croft, Lehman, and Magidor. Okay.
Yeah, their work has really shaped the field, and it's led to a ton of research exploring different aspects and extensions of their framework.
What kind of extensions?
Well, some researchers have extended it to first-order logic, which is a more expressive logic than propositional logic.
Right. Propositional logic just deals with simple propositions,
Yeah.
like P and Q. But first-order logic lets you talk about objects and properties and relations.
Exactly. So extending selection semantics to first-order logic makes it much more powerful.
I could see that. What else?
Well, others have looked at alternative semantics that validate weaker properties than rational monotony.
Okay, because rational monotony isn't always appropriate.
Right, exactly. And there's also been a lot of work connecting selection semantics to conditional logic.
Conditional logic, so that's the logic of if-then statements?
Right, and it's really important for understanding how we reason about hypothetical situations and counterfactuals.
So, like, what would have happened if things had gone differently?
Exactly. It's all about exploring the different possibilities and consequences of our actions and choices.
This is fascinating. It's like this one framework. Selection semantics has opened up a whole universe of possibilities for studying non-monotonic reasoning.
It's really a foundational framework, and it's still an active area of research today.
That's amazing. Okay, but now I'm remembering another challenge that we talked about earlier, the issue of relevance,
Oh, yeah,
like
right.
in the Nixon Diamond example.
Yes, where we wanted to be able to conclude that Quaker and worker implies pacifist, even though worker seemed irrelevant to the connection between Quaker and pacifist.
Exactly. It felt like a reasonable inference to make. But the standard rational consequence relations don't always capture that kind of inference.
You're right, they can get tripped up by irrelevant information.
So how do you address this issue within selection semantics?
Well, one solution is to use a more refined notion of closure called rational closure.
Rational closure, okay.
It was developed by Lehman and Magidor, and it's basically a way of ranking formulas based on how exceptional they are.
Exception. Okay, so like how much they deviate from the norm.
Exactly. So in our Nixon Diamond example, the formula Quaker and worker would have a pretty low exceptionality ranking.
Right, because it's not that unusual for a Quaker to also be a worker.
Exactly. It's a fairly normal combination of properties.
Okay, so how does this ranking help with the issue of relevance?
Well, rational closure uses this ranking to determine which conclusions are justified.
Okay.
So in our example, the conclusion Quaker and worker implies pacifist would be in the rational closure.
Because it's more normal for a Quaker who's also a worker to be a pacifist.
Exactly. It's less exceptional than the alternative.
Okay, I think I'm getting it.
It's basically a way of filtering out the irrelevant information by focusing on the formulas that are most likely to be true in the most normal worlds.
And that's how it avoids those counterintuitive conclusions that can arise from irrelevant information.
Precisely. It's a very clever solution, and it's been quite successful in capturing a wider range of intuitive inferences.
So it's like selection semantics is getting smarter and smarter.
You could say that it's constantly being refined and extended to handle more and more complex cases.
Okay, so rational closure is a refinement of selection semantics, and it helps address the issue of relevance. But are there any other refinements or extensions that are worth mentioning?
Definitely, there's a whole lot more to explore.
Like what?
Well, for one thing, rational closure itself has been the subject of further research and refinement, for instance. It's been shown to be equivalent to another system called System Z, which uses conditional probabilities to define non-monotonic entailment.
Conditional probabilities. Okay, so that's like looking at the probability of a conclusion given the premises.
Exactly. And it's really interesting to see how these two seemingly different approaches, one based on ranking formulas and the other based on probabilities, end up converging on the same set of conclusions.
It's like they're different paths leading to the same destination.
Precisely. And it speaks to the deep connections between different formalisms in non-monotonic logic.
This is so cool. It's like we're uncovering a hidden network of relationships between all these different ideas.
We are, and it's one of the things that makes this field so exciting.
Okay, but now I'm remembering something we talked about earlier, the drowning problem.
Oh, the drowning problem, yes.
I thought we had left that behind with those simpler, skeptical reasoning approaches.
It's a tough one to get rid of completely.
So is rational closure vulnerable to the drowning problem too?
Unfortunately, yes, it can still sometimes be too cautious and reject plausible conclusions.
Oh no, so we're back where we started.
Not quite. There's another refinement that specifically addresses the drowning problem in the context of rational closure.
Okay, what's it called?
Lexicographic closure.
Lexicographic closure.
It was developed by Lehman, and it's a really clever solution.
So how does it work?
Well, it basically introduces a more fine-grained way of comparing models.
More fine-grained than what?
Then rational closure. Rational closure just looks at the number of exceptions a model violates.
Right.
But lexicographic closure also considers the severity of those violations.
Okay, so what makes one violation more severe than another?
It's all about specificity. Violating more specific conditionals is considered more severe than violating more general ones.
Oh, that makes sense.
Right, it's like saying it's better to break one general rule than to break multiple specific rules.
Because breaking those specific rules suggests a more serious departure from normality.
Exactly, and lexicographic closure takes this into account. When comparing models, it prefers models that violate fewer specific conditionals, even if they might violate more general ones.
So it's like it's trying to find the best balance between respecting exceptions and generalizing from them.
It's a very nuanced approach, and it's been shown to be very effective in handling a wide range of examples that were problematic for rational closure.
Wow, so lexicographic closure is like the ultimate refinement of selection semantics.
You could say that it's the culmination of a lot of research, and it really pushes the boundaries of what we can express and reason about in a non-monotonic framework.
This is incredible. It's like we've gone on this amazing journey through the world of non-monotonic logic.
We have, and we've seen how these different formalisms have evolved over time to capture more and more of the subtlety and complexity of human reasoning.
And it's all based on this core idea that our beliefs are defeasible, that we can change our minds when we get new information.
That's the heart of it, and it's what makes this field so fascinating and so relevant to understanding how we think.
Okay, so we've covered a lot of ground today, but there's one more family of approaches that I want to make sure we touch on before we move on.
All right, what's that?
Assumption-based approaches.
Oh, yes, those are a good one. They take a slightly different perspective on non-monotonic reasoning.
How so?
Well, instead of focusing on defaults or preferred models, they focus on making assumptions explicit.
Explicit assumptions. Okay, so like spelling out the conditions under which a conclusion holds true.
Exactly. It's like saying, if this is true, and we assume that this other thing is also true, then we can conclude this.
So it's all about transparency and making sure that the assumptions are out in the open.
Exactly. And it turns out that this approach can be very powerful and very elegant.
Okay, I'm intrigued. Tell me more.
Uh,
Okay, so assumption-based approaches, it's all about making those assumptions explicit, bringing them out into the light.
exactly. It's like saying, hey, we're making these assumptions. Let's acknowledge them and see how they affect our reasoning.
I like that it seems very honest and transparent.
It is. And it can be very powerful because it allows you to manipulate and reason about those assumptions directly.
Okay, so can you give me an example of how this might work in practice?
Sure, imagine you have a rule like birds fly.
Right, a classic.
But in an assumption-based approach, you would represent this as something like, if X is a bird, and assuming A, then X flies, where A is an assumption like, there's no reason to think this bird can't fly.
Okay, so you're basically adding an explicit assumption to the rule.
Exactly. And then if you later learn that the bird is a penguin, you can retract that assumption and revise your conclusion.
Right, because the penguin exception would violate assumption A.
Exactly. And that's one of the beauties of this approach. It gives you a very clear and systematic way to handle exceptions.
It's like a built-in mechanism for revising your beliefs when you get new information.
It is. And there are several different formalisms that implement this assumption-based approach, each with its own unique features.
Okay, like what are some of the key players in this realm of assumption-based reasoning?
Well, one of the most prominent is adaptive logic.
Adaptive logic, okay.
It was developed by Diderik Battens, and it's a really elegant framework.
So how does adaptive logic work?
It starts with a base logic, which defines the basic non-defeasible rules of inference.
Non-defeasible. So those are the rules that are always true no matter what.
Exactly. And then it adds a set of abnormalities, which are formulas that we want to treat as false as much as possible.
Okay, so abnormalities are like potential exceptions to the rules.
Exactly. And adaptive logic uses a dynamic proof theory to reason about these abnormalities.
A dynamic proof theory. Okay, so what's dynamic about it?
It means that the proof can evolve over time as new information comes in.
So it's not like a static proof where you just write down the premises and the conclusion and you're done.
Right. It's more like a process of discovery where you're constantly testing and revising your assumptions.
Okay, I'm starting to see how this relates to non-monotonic reasoning.
It's all about being able to adapt to new information and revise your beliefs accordingly.
And how does adaptive logic handle this dynamic process?
It uses a marking mechanism where lines in the proof can be marked as in or out, depending on whether the assumptions they rely on are still considered valid.
So it's like a constantly evolving web of beliefs, with some lines being activated and deactivated as new information comes in.
That's a great way to put it. And different adaptive logics use different strategies for marking and unmarking lines, which leads to different levels of cautiousness in their reasoning.
So some are more eager to jump to conclusions while others are more conservative?
Exactly. And this flexibility is one of the strengths of adaptive logic. It allows you to tailor the reasoning process to the specific application.
Okay, so adaptive logic is one approach to assumption-based reasoning. What are some others?
Well, another influential approach is the idea of default assumptions, which was developed by David Mackinson.
Default assumptions?
Yeah, it's similar to adaptive logic in that it uses sets of assumptions to encode defeasible inferences.
But it uses a different mechanism.
It does. Instead of marking and unmarking lines, it uses the concept of maximally consistent subsets.
Maximally consistent subsets. Okay, now that sounds like a mouthful. What are those?
Yeah. Basically, it's about finding the biggest chunk of information you can take from the original set of formulas without running into any contradictions.
Okay, so it's like finding the most consistent interpretation of the available knowledge.
Exactly. And in Mackinson's approach, a conclusion is considered a default consequence if it follows from all the maximally consistent subsets of the premises and assumptions.
So it's like saying, no matter how I slice and dice the information, as long as I stay logically consistent, this conclusion always holds true.
Precisely. It's a very robust form of inference, and it has some interesting connections to both adaptive logic and preferential semantics.
It's amazing how all these different threads keep coming together.
I know. It's like we're weaving a tapestry of non-monotonic logic.
And each thread adds a new layer of richness and complexity.
Exactly. And speaking of richness and complexity, there's one more assumption-based approach that I want to make sure we touch on before we wrap up.
Okay, what's that?
Conditional entailment.
Conditional entailment.
It's a really elegant approach that was developed by Hector Geffner and Judea Pearl.
Okay, so what makes conditional entailment special?
Well, it brings a particularly nice way of handling specificity to the table.
Specificity. Okay, we've been talking about that a lot today, but remind me why it's so important.
Well, it's all about prioritizing more specific information over more general information when we're reasoning about the world.
Right, like with the birds and penguins.
Exactly. And conditional entailment does this by introducing an ordering on the assumptions that reflects their specificity.
So more specific assumptions are given higher priority.
Exactly. And this ensures that the system respects exceptions and inheritance in a way that aligns with our intuitions.
Okay, so can you walk me through an example of how this works?
Sure. Let's say we have our bird rule again. If X is a bird and assuming A, then X flies.
Okay.
And then we have a more specific penguin rule. If X is a penguin and assuming B, then X doesn't fly.
Okay, so assumption B is more specific than assumption A.
Exactly, because penguins are a specific type of bird, and conditional entailment uses this specificity ordering to define a model comparison relation that prefers models where more specific assumptions hold.
So if you have a model where both a penguin and a robin are birds,
Right.
the model where the penguin doesn't fly and the robin does fly would be preferred.
Exactly, because it respects the more specific penguin rule.
It's like the penguin rule overrides the general bird rule in that context.
Precisely, and this elegant handling of specificity is one of the key strengths of conditional entailment.
It's like the system has a built-in understanding of how exceptions and inheritance work.
That's a good way to think about it, and it makes conditional entailment a very powerful tool for modeling common sense reasoning.
Wow, so we've covered a lot of ground today. We've explored the closed world assumption inheritance networks, default logic, autoepistemic logic selection semantics, and now assumption-based approaches.
It's been quite a journey.
It has, and it's amazing to see how all these different formalisms have been developed to capture the nuances of non-monotonic reasoning.
It really is a testament to the power of logic and the ingenuity of the people who work in this field.
And I think it's also a testament to the complexity of the human mind.
Absolutely. We humans are incredibly good at reasoning with incomplete and changing information. And these formal systems are helping us to understand how we do it.
And to maybe even do it better.
Perhaps, who knows what the future holds for non-monotonic logic.
Well, I, for one, am excited to see where this field goes next.
Yeah.
It's clear that there's still so much to explore and discover.
I agree. It's a fascinating and rapidly evolving field, and I have a feeling that we're only just scratching the surface.
So to our listeners out there who are now intrigued by this world of non-monotonic logic,
Right.
Where should they go to learn more?
Well, I'd say a great starting point is the Stanford Encyclopedia of Philosophy entry that we've been discussing. It's a really comprehensive overview of the key concepts and formalisms.
It's dense, but it's worth the effort.
It is, and from there are many excellent textbooks and research papers available both online and in libraries.
And don't be afraid to get your hands dirty, experiment with different formalisms, play around with different reasoning patterns.
Absolutely, the world of non-monotonic logic is full of surprises and waiting to be explored.
So keep those minds flexible, those assumptions revisable, and those inferences defeasible.
Happy reasoning, everyone!
And on that note, we'll wrap up our deep dive into the fascinating world of non-monotonic logic. We hope you enjoyed the journey and learned something new about the logic of human thought, both its strengths and its quirks. Until next time, keep those minds curious and those inferences flowing.